Kia ora koutou, nau mai, haere mai. Welcome to lesson 17 for introductory physics. This lesson is going to define collisions. We've essentially met collisions already. At the end of the previous lesson, we talked about the idea of two objects crashing into each other. That's what we're talking about when we talk about collisions, but we're going to define the term exactly and talk about some examples of it. As usual, we'll jump over to the slideshow and have a look through. So lesson 17, collisions. Our goal is to define collisions and then use the idea of conservation of momentum to solve some simple one-dimensional collision problems. In the next lesson, we will expand that to look at two-dimensional problems because, as we saw, momenta are vectors, and that means we can deal with 2 or 3 dimensions quite easily using all the vector maths tools that we've already worked through. We're going to, that next point shouldn't actually be on this slide, defining the components, decomposing the components is part of next lesson, so apologies for not removing that, but we will define elastic and inelastic collisions and look at determining whether they are collisions that are elastic or inelastic in any given scenario. So to start with, what is a collision? First of all, it's still very important to define our frame of reference. We need to define our positive x and y. With one-dimensional, it's very simple because we can just use plus and minus as we've already seen. So all the exact same things that I've been saying right throughout the course, I'm going to keep saying. You need to define your frame of reference, and if it's one-dimensional, great, just choose a plus and a minus direction, you're done. If it's two-dimensional, define your x and your y and your plus and minus for each of those directions. The concepts, of course, do work in 3 dimensions, but again, we still won't really go into 3D just because the maths gets more cumbersome. The physics is the same. The idea of thinking about the scenarios is exactly the same. So you certainly could do 3-dimensional problems, but the maths is just more messy and more involved, so we don't bother with that. So what does a collision actually mean? A collision in physics is pretty much the same thing as you're used to with the term collision in everyday life, but we do have one little clarification as to whether or not something counts as a physics collision, and that is that a collision is an interaction between 2 or more objects throughout which the impulse on the system due to external forces is negligible. Right? So we have to define the system, and the system involves the objects that are colliding, always involves both of them, because if it was only one of them, the other object colliding with it would be an external force, so it definitely isn't a collision. But as long as the system involves both of the objects that are colliding, then it's going to be, then it can be counted as a collision, but it can't have any impulse on the system. So it can't have a net force on the system because a net force over time is an impulse. A net force for some amount of time is an impulse. So we can't have that. There can often be net external forces leading up to a collision and again on the objects after the collision. But during the collision, the impulse from any external force should be negligible. Remember that an impulse is a force times a time, force multiplied by time. So that means either the force has to be 0 or close to 0, or the duration of the collision, that time, has to be close to 0. So that's what an impulse, that's what the impulse being 0 means. It means either the force is pretty much nothing, or the time of the collision is pretty much nothing. We're going to define all of these terms now. Total momentum of our system is conserved during a collision. If there's no impulse, if there's no net external impulse, then there can't be a change in momentum, because remember, change in momentum is equal to that impulse. So if there's no net external forces or no time, then our impulse is pretty much 0, and that means that our change in momentum is pretty much 0. So as long as there is no external impulse, we can't have a change in momentum, and that means that the conservation of momentum applies to physics collisions. Right? When we talk about collisions, we always talk about the initial and final momentum or velocity or kinetic energy. Initial and final. That means that we have to have a start point and an end point for our collision. It doesn't make sense to talk about initial and final if you don't have a start and an end point that we're talking about for those initial and final values. The start time is the instant the objects come into contact. Technically, it's the instant before that. It's as soon as they touch. They haven't had any changes to their velocities or anything yet. So they're still at their initial velocities, still at the velocity they're traveling at before the collision. The instant they're about to come into contact, but we haven't yet accounted for any actual change in velocities or momentum or anything from the collision, that's what we're talking about for the initial values. The end time, the final values, occur at the moment the objects stop having any kind of effect on each other. which is usually the instant they separate, but sometimes they don't actually separate. So we'll talk about that a bit more now. First of all, let's think about two really rigid objects. So this is our classic example of something like two billiard balls colliding. When they bounce off each other, there's pretty much no time of impact because the balls don't change shape. They just touch for an instant and then they separate again. So in that case, the duration of the collision is practically zero. The balls aren't really in contact for any finite amount of time. It's an instantaneous bounce and then nothing. So that means that the instantaneous collision means that that initial time and final time are kind of actually almost at the same point. We've got an instant before they collide, an instant that they are colliding, and an instant after they collide. And that's our initial and our final, either side of that collision. So it's very little duration, practically zero. In reality, it's never going to be exactly zero. If it were zero, then there would be no time for the objects to have any kind of effect on each other. But it's so close to zero as to be able for us to say that it's zero. However, if the two objects are sort of squishy, you can imagine two sort of bouncy balls or even blobs of putty or something, then they might separate still, but they might come into contact and sort of squish for a while, and there's actually a significant duration of collision. So that's this example here. You've got these two balls, they still collide and they still bounce away from each other, just like we saw with the rigid collision, the one that had no time of collision. But for this, in this scenario, we do have a duration to our collision. So those two balls are in contact for some period of time. What that means in terms of what we just said about not having any impulse, net impulse, is that the net external force must be zero because now there is time for that external force to act. So we would need net external force to be zero in this case. Defining contact duration, what you can see here is I've just sort of drawn snapshots of that system. At the top, the balls are far away, they're moving together. At that first dashed line is when the balls first come into contact, so they just touch, but they haven't yet had any effect on each other. They haven't started to change shape, they haven't started to change velocities, they haven't had any effect. They are just right at that very instant of very first contact before they've really had any impact on each other. And at that point, that's when we define our initial time. And so our initial velocities are the ones they have right at that instant. The initial momentum is what they have right at that instant. The initial kinetic energy is what they have right at that instant. Then the balls start having an effect on each other. They squish up a bit, and then they separate a bit as they start to bounce off each other. And that second dotted line is at the instant that the balls are only just touching for the very last moment. And after that, the balls are separated and they travel off on their own paths. That second dotted line is the final time. So that point, that instant, is what we define for the final velocities, final kinetic energies, final momenta. The difference in time between that initial time and that final time, that's the duration of the collision. As I said, this one, they are in contact for some duration. For the previous one, the balls basically just touched and then separated again. So there would only be one dotted line, and it would be the initial and the final. Everything sort of happens in that one instant. But when we've got a duration, it looks something more like this. If the two objects stick together, though, then that means that they've both stopped moving, or they might keep moving, but they'd be moving together as one object now. And sometimes this might still have negligible duration. Sometimes two objects just collide and stick. So you can imagine a couple of big magnets moving towards each other. They collide and they just stick together. There's no deformation. There's no time to worry about. It's just they're not stuck together, and then suddenly they are stuck together, and that's it. There's no duration. But there are plenty of examples where there is a duration as well. And again, we can think about that contact duration or collision duration. Sorry, not contact duration. The collision duration as being from the instant they first come into contact, so before they have any effect, but their very surfaces just start to touch. That's our initial time. The final time is a bit harder to define in this case, and it's definitely very difficult to measure. We can't usually actually measure it. It's pretty impractical, but we can still theoretically define it, and it is the point at which the objects stop having an effect on each other. So if you've got two balls that are deforming as they collide and then sticking together, the final time, the time of the point that we would define as final for the purposes of defining our momenta, kinetic energy, and velocity, is the instant at which the balls stop having an effect on each other. Even though they're still stuck together now, they were affecting each other through that deformation, So the instant at which that deformation finishes, that's the final time. So from then on, the balls aren't changing shape or being deformed in any way anymore. So we can still define that duration of collision exactly the same as before. It's just that after the collision now, the balls are moving together as one object rather than as two separate objects like we saw before. So when we talk about initial, as I said, it's everything at that TI, the instant of TI, when they first come into contact. In many cases, the momentum before the collision is not changing, so you can calculate at any point. You could calculate it right at the top of that, that very first snapshot I've got there. If the velocity of each object is not changing on their approach to that collision, you can calculate it at any point. But in a lot of cases, the momentum is changing as the objects approach that collision. So there might be two cars that are accelerating right up to the instant of the crash. And remember, acceleration can be a deceleration as well. So there might be two cars braking as they approach a collision. So you can certainly have those velocities changing in the lead up to a collision. And that's why we define that initial time as the instant they come into contact. Because it doesn't matter what the car was doing or the object was doing before that. It doesn't matter if it was getting faster or slower or turning a corner. It doesn't matter. All that matters is what its velocity was right at that instant is known, so that we can use that to determine the initial momentum of the object for that collision. So when we talk about initial for a collision, we mean right at the instant that they first come into contact. We don't care about the history of it before that, and that's for both objects or however many are involved in the collision. And then the final, again, is the same thing. The final momentum is exactly the same, but it's right at that instant of TF, the moment they stop having an effect on each other. Again, there are scenarios where there will be forces on the object straight after that. A car crash, the cars are deformed, they're scraping on the ground, there's friction and so on. There will very likely be external forces, and the momentum is going to change. The cars might come to a stop very quickly afterwards. But if the collision itself had no change in momentum, you can still define that TF and analyze it as a collision. As we saw in the previous lesson, there are plenty of times where a crash is not a physics collision because that external force does have an impact. So to be very clear, if delta T is about 0, external forces are irrelevant. They don't have time to act on our system. Remember that a change in momentum needs a force applied over a period of time. If delta T is pretty much nothing, then that force does not have time to act, so it doesn't really change the momentum. It doesn't have time to change the momentum, so it doesn't matter if it's present, because the momentum from TI to TF, because that's all we care about. We don't care about before TI or after TF. The momentum from TI to TF doesn't change. And if it doesn't change, then we can treat it as a physics collision and assume the momentum is constant right throughout. However, if delta T is greater than 0, if it's not negligible, then that means we have to have net external force of close to 0, practically 0. Because if the force wasn't practically 0, the impulse would be non-negligible. We would have a non-zero force times a non-zero time, which would give us a non-zero change in momentum. And that means that our system would be changing momentum due to an external force, and it's no longer a physics collision. Remember that the total momentum is the sum of each object in a system, and momentum is a vector, so we need to do vector addition when adding momentum. We're looking at one-dimensional problems mostly. Apparently I have included some two-dimensional stuff in here, but we talk more about two-dimensional collisions in the next lesson. So in this case, the total momentum of these two cars is that red vector, and it remains unchanged before and after the collision. Right? The total momentum before and after the collision is unchanged because it's a collision, which means no net external force, which means the total system momentum cannot change. So the idea of conserving momentum gives us another alternative definition for collision, and that is to state that a collision is an interaction between two or more objects throughout which the momentum is conserved. That's exactly the same as what we said before. If there is no net impulse on the system, then impulse is change in momentum. So if there's no impulse, there's no change in momentum. No change in momentum is just the same as saying it is conserved. So it's exactly the same definition, just worded differently. Total momentum of a system doesn't change, right? And that means we can solve problems about momentum using, using the conservation of momentum when we have a collision. For example, we've got two identical balls here. They're different colors just to differentiate them, but they're identical balls. One is traveling at 5 meters per second towards the other, which is at rest in our frame of reference. They collide, and then after the collision, the first one that was moving is now stationary, and the second one is now moving at 5 meters per second. We know that second one must be moving away at 5 meters per second, even if they hadn't told us, because momentum has to be conserved. We're told it's a collision, therefore momentum can't change, and if the two balls are identical, then momentum of whatever the mass of the ball is, m times 5, so 5m initially, means we must have momentum of 5m in the final scenario, which means that second red ball must be traveling at 5 meters per second. So we can solve simple collision problems using this idea of conservation of momentum. If we know the initial velocities and we know one of the final velocities, we can figure out the other final velocity, or vice versa. As long as you know 3 out of the 4 velocities, and you've got 2 initial and 2 final, as long as you know 3 of them, you can figure out the 4th one. The next part is to consider energy during collision. So we've been talking about momentum so far. We also have to think about energy. Energy during collisions, is it conserved? The answer is it depends. Sometimes we have what is known as an elastic collision. So elastic collisions are ones that do conserve kinetic energy. The kinetic energy initially is the same as the kinetic energy finally. Remember that initial and final are still defined the same way we just spent a bit of time discussing. There's still that instant at the first contact and the instant of final contact. Those are our initial and final. So initial kinetic energy and final kinetic energy are the same in, I shouldn't say inelastic, I should say for elastic collisions, just to avoid ambiguity. So for elastic collisions. For inelastic collisions, kinetic energy is different. Now we know that we can't create energy, and assuming we have no net external force, because we said that there is no impulse, no change in momentum, if we have no net external force, then we can't gain energy either. But what we can have is kinetic energy being lost through deformation of the objects involved, or potentially sound being sent off into the environment, or occasionally light. That means that our objects can lose energy. They can lose energy, which means kinetic energy can decrease. And if kinetic energy does decrease, then it is an inelastic collision. So inelastic means energy is lost. Elastic means that it is conserved. An example we saw before, where we had a ball traveling at 5 meters per second and then the other one traveling at 5 meters per second, the kinetic energy there is conserved. It's exactly the same to start with. Remember, our ball was just some random mass m, so our initial kinetic energy is a half m times 25. And a half m times 25, so 12.5 m for our initial kinetic energy, and our final kinetic energy is exactly the same, half m times 25, which is 12.5 m. So our kinetic energy is the same before and after, therefore it's an elastic collision. For an inelastic collision, as I said, it goes other places. It can be lost to permanent deformation of the object, or to the generation of heat or noise or sound or vibration, or occasionally light, although that's not as common. In a perfectly inelastic collision, the objects will stick together and move as one after the collision. So momentum is still conserved. Momentum is always conserved if it is a collision. That's how we define collision for physics. So if we are talking about a physics collision, then momentum is being conserved. However, the kinetic energy isn't always, and you need to know a little bit more to be able to determine what the final kinetic energy would be. And that includes things like, is it elastic or inelastic, or just getting the values and calculating it and determining whether it's inelastic or elastic. So this little table is pretty much a summary of what we've just said. For an elastic collision, both momentum and kinetic energy are conserved. For an inelastic collision, momentum is still conserved, it's still a collision, but kinetic energy is not conserved. Now, one thing that I haven't put in these slides, but I will just mention, is that it's a spectrum. Kinetic energy can be anywhere from going all the way to 0 to remaining exactly the same. So exactly the same means it's an elastic collision. Going all the way to 0 is our perfectly inelastic collision, or some minimum amount is our perfectly inelastic collision. But it could end up anywhere in the middle. It could be halfway between the initial and what it would be if it was perfectly inelastic. So elasticity of a collision is not a yes or no thing. It can be anywhere on a spectrum. So we always have elastic being perfectly conserved. Everything else we call inelastic. But sometimes you'll hear the term perfectly inelastic, which is where they stick together and travel off, and that's the minimum amount of kinetic energy that the system could have after that collision. You don't need to worry too much about that, but just being aware of that when we say perfectly inelastic, that's why we say perfectly, because you can have an elastic that's not perfect. So to finish off, we'll work through a few examples just to look at a couple of one-dimensional collision problems. So firstly, two billiard balls. As I've said, billiard balls are a sort of a classic example because they do fairly nice elastic collisions. In the following two scenarios, all the balls are 162 grams. Both collisions are perfectly elastic. Determine the total momentum of the system before and after and show that it is conserved. So we're told it's conserved, but this is just some calculations to double check. So I'm not actually going to work through this one for you. I'm not going to do it on the document camera, that is. The solutions are on the next slide, so I recommend you pause the video now and just do those calculations. Calculate the initial and final momentum for the system and the initial and final kinetic energy for the system. Actually, it doesn't ask about the kinetic energy. It's only asking for the momentum. So find those values for these two systems. So do that now. Once you're finished, resume the video and we'll have a look at the answer slide. So here it is. For the first scenario, scenario A, we have the before momentum as being the sum of the two initial momentums. One of them is 0 though, so that's pretty easy. So we have 162 grams times 4 meters per second is 0.648 kilogram meters per second. And afterwards, it's actually the exact same calculation. The masses are the same, but we've now just swapped the velocities. But since the masses are the same, it doesn't make any difference. So of course, the same calculation will give us the same answer of 0.648 kilogram meters per second. Exactly the same, so momentum is conserved. The second scenario, again, we're just swapping velocities essentially. Right? We're swapping velocities. We have the first one going at 6, the second one going at 1 meter per second. After the collision, they've just swapped. The first one is now only going at 1 meter a second, and the second one is going at 6 meters a second. And because they all have the same mass, again, that calculation is exactly the same. We've got 0.162 times 6 plus 0.162 times 1, and that gives us 1.134 kilogram meters per second. So of course, 0.162 times 1 plus 0.162 times 6 is going to give us the exact same answer. So momentum is again conserved. So hopefully nothing too surprising there, just a bit of practice at doing that calculation, and hopefully you can see why I didn't bother doing that on the document camera. The next example is we've got two balls. One is a golf ball of mass 45.9 grams moving at 7.66 meters per second to the right, and that golf ball collides with a Pétanque ball. It has a mass of 792 grams, and it was at rest initially. Afterwards, the golf ball bounces off the Pétanque ball and it heads back to the left at 1.63 meters per second, and we have been asked to determine the velocity of the Pétanque ball after the collision. So this one I will work through on the document camera. This is quite a standard sort of problem. You should certainly be able to work through one like this. We'd definitely expect you to be able to handle this sort of problem. So as usual, first thing is a good idea to start with is to draw a little sketch. So we've got a golf ball and we've got a Pétanque ball. The Pétanque ball is much bigger than the golf ball. We need to define our frame of reference. I'm going to define positive to the right and negative to the left. We've got the mass of our golf ball as being, 45.9 grams, which is 0.0459 kilograms. And for the Pétanque ball, our mass was 792 grams, or 0.792 kilograms. Obviously, everything needs to be in SI units as usual for collisions, for calculating momentum and kinetic energy. We then have the initial velocity of the golf ball. So I'm going to do velocity of the golf ball initially, so double subscripts there, golf initially, is equal to positive, because it's moving to the right, positive 7.66 meters per second. The initial velocity of the Pétanque ball was equal to 0 meters per second. It was at rest. The final velocity of the golf ball, VGF, was equal to negative 1.63, I think it was. I'll just double check that. Yep, negative 1.63 meters per second. So negative because it's moving back the other way. It goes this way and then bounces back, whereas the Pétanque ball starts moving forward. So what we're looking for is the final velocity of the Pétanque ball, the Pétanque final velocity. That's what we're looking for. Now, what we know is that it's a collision. We've been told it's a collision. I think we said it was a collision. Did I say? I did say golf ball collides with a Pétanque ball in the text of the question. So we're told it's a collision, which means momentum is conserved. So what we know is that the total momentum initially is equal to total momentum finally. Right? That's what we're told. This is the conservation of momentum because it's a collision. Right? So that's the bit of information we have that will allow us to solve this problem. If we didn't know that, if we didn't know it was a collision and we didn't know the momentum was conserved, we'd have no way of figuring this out. But because we know it's a momentum conservation scenario, it means we can figure this out. So let's think about our momenta. This one, we just do our mass times our velocity, so 7.66 times 0.0459, and that gives us momentum for the golf ball initially as those two multiplied together, which is 0.35, I'll just go 352 kilogram meters per second. And the Pétanque ball has an initial velocity of 0. So it doesn't matter what the mass is. If the velocity is 0, then the momentum of the Pétanque ball initially must be 0 as well. So that's 0 there. The final velocity of the golf ball is negative 1.63. So the momentum is going to be 0.0459 times negative 1.63, which is negative. So golf ball finally is negative 0.075 kilogram meters per second. We don't know the final Pétanque momentum. We don't know that one. But since we know these three and we know the total momentum is conserved, then that means that if we add the two initial momentums together and get our total to start with, that's the same, must be the same as these two final ones. So we've got 0.352 and 0. So the total in there is obviously 0.352. That means the total here has to be 0.352 as well. So if the total is 0.352, and we know that the momentum of this one is negative 0.075, then we can just do 0.352 minus negative 0.075 and get a final momentum of 0.427 kilogram meters per second. So that's our final momentum. And then if we know the momentum, we just divide by velocity, divide by mass to get the velocity. So if we divide by the mass, which was 0.792, so that divided by 0.792 gives us a final velocity of 0.538 meters per second. So 538 meters per second, or 539, depending on how we rounded. I've rounded a bit much, so I've ended up with a slightly off answer. Should be 538 rather than 539. But that's our final velocity. And that's the approach, right? To figure out the total momentum, knowing that it's conserved, you can use that to say the final is the same, which means if you know the momentum of one of them, you can figure out the momentum of the other one. And if you know the momentum, then you can figure out the velocity based on the mass. So that's the whole process for figuring out a scenario like that. And it's very common, those sorts of problems you shouldn't have any problem with. So just repeat them until you get confident with them. The final velocity was what we're looking for here, but there are also plenty of scenarios where we're looking for initial, and we'll give you both finals and one of the initials and things like that. So dealing with any scenario like that is one that you want to be confident in. As usual, that is all included in the lecture slides. The answer is right there. We saw that the golf ball and the Pétanque ball ended up at those different velocities. We now want to determine if the collision was elastic. So was that collision elastic? How do we do that? Well, we just check whether the kinetic energy was conserved. If it was conserved, so the same initially and finally, then the collision was elastic. If it changes, it's inelastic. So let's have a look. I'm not going to do this on the document camera because it's purely calculation. Just calculate the kinetic energy initially of the golf ball. It comes out to be 1.347 joules. The kinetic energy of the piton ball initially is 0 because it was at rest. And then we've got the after kinetic energies. Remember that kinetic energy is always positive and it's just a scalar, right? There's no such thing as negative energy, and it doesn't have a direction, just a magnitude. So we don't really have to worry about which direction the velocity is in. All we care about is that magnitude of the velocity. So we can ignore all the plus and minuses from our frame of reference. And we see that the after energy is 0.061 joules for the golf ball and 0.115 joules for the pétanque ball, which is a total energy of only 0.176 joules. And our initial kinetic energy was 1.347 joules. So clearly the kinetic energy is much less afterwards, and therefore it's an inelastic collision. We have an inelastic collision. It doesn't change the answer to the previous slide. We still have the exact same answer as we did before for that momentum question, because momentum is always conserved in any collision. We just now know that it was an inelastic collision because that kinetic energy changed. And that means that something about the balls changed. As they collided with each other, there was some kind of deformation process that happened inside the object as well. Or it could have been just sound. Wouldn't lose that much likely to sound. It's most likely going to be some kind of deformation. So potentially the golf ball squashed as it collided with the pétanque ball and then started sort of oscillating or vibrating in some way, something like that. We don't need to worry about the exact details. Just being aware that we have lost that energy is the goal. The last example, I think it's the last one, is inelastic train cars. Two train cars on a track. The first one has a mass of 62,000 kilograms, moving right at 13 meters per second. The second one has a mass of 59,000 kilograms and it's stationary. They collide. It's an inelastic collision, so the train carriages couple together, they latch together and move off as one unit. What is the velocity of the coupled cars after the collision? I could do this one on the document camera, but instead I'm going to recommend that you pause the video and have a go at it yourself. At this point, you should be pretty confident with this sort of problem solving. It's exactly the same as what we saw before, but what you'll notice is that we haven't given you either velocity afterwards, but we've told you they are both the same. So if you figure out the momentum initially and the momentum afterwards, excuse me, then you know that the momentum afterwards is going to be coming from an equation that has velocity final for both train cars being the same. So do pause the video and have a go, and now we'll work through the answer. So again, frame of reference, we're going to define right as positive. Nothing ever moves left. The first car is moving towards the right, it collides with the second one that's at rest, and then they both move to the right. So nothing ever moves left, so everything positive for this scenario. If we had defined right as negative, then everything would be negative and it would be the same calculations. Beforehand, the momentum is just the momentum of the first car because the second one is 0, and that is 62,000 kilograms times 13 meters a second, which is 806,000 kilogram meters per second. Afterwards, as I said, we know that the final velocity for both cars is the same. That means that m1 times final velocity plus m2 times final velocity is our total momentum after the collision. Because that final velocity is the same for both of them, we can actually just factor that out. So a little bit of math, factor out the VF and rearrange, we get net momentum or total momentum divided by the total mass gives us the velocity of the train cars after the collision, and it comes out to 6.7 meters per second. So 6.7 meters a second for that final velocity. So that's the end of this lesson. As I said, it was just looking at one-dimensional collisions, although I did mention vector decomposition as a reminder that momenta are vectors, but for 1D, obviously that just means plus or minus. In the next lesson, we will look at two-dimensional collisions, and so in that case, it's even more important to recall that we have momenta as vectors, and you're going to need to decompose them in order to do your collision analysis.